doing section 4.3, example 4. It's a word problem, so we can read through it. A stone is thrown into a pond and circular ripples expand away from the point that the stone hits the water. The radius in feet of one of the ripples is given by this function here. R of t is equal to 3t. T is measured in seconds. Find the rate of change of the area enclosed by the ripple. Okay, so we're going to sort of put this together with two different functions, the radius function, and then we're going to have a different function for the area, since that's what they're actually asking for. So first we'll notice that this function here gives us the radius at any time t. If I want to know what the rate of change of that is, I take the derivative. The derivative is the rate of change. So this is the derivative of the radius with respect to time. As we know from the power rule, that's just going to be 3. So feet per second. Notice that with the Leibniz notation, you can really kind of see why this notation is good. dr dt, the units of r are feet, and the units of t are seconds. And then notice that the units of the final derivative here are 3 feet per second. So the notation will help you to see what the units have to be. Okay, and then for each foot that the radius increases, so in other words, if I have a 1 foot increase in the radius, then the area is going to increase by 2 pi r feet squared, because the area of a circle is 2 pi times the radius. So another way that we can look at that is that the area will change by 2 pi r square feet for every 1 foot change in the radius. So again, if we read what it says here, for each foot that the radius increases, so that would be this, each foot that the radius increases, the area is going to increase by 2 pi r feet squared. We can look at this in terms of derivatives by saying dA dt is equal to 2 pi r, and then the units on this are feet squared per foot. That's kind of a strange unit, but the way that we can interpret this, oops, sorry, this should be dA dr, not dA dt. Let me fix that. And then I'll try to explain why the units are the way they are. So this is dA dr. So again, look at what we have on the bottom here. This is saying that for every 1 foot change in r, in other words, for every 1 foot increase of the radius, the area is going to increase by that much. Again, that's because the area of a circle is 2 pi r. And again, look at the units here. For a 1 foot change in the radius, the area is going to increase by 2 pi r square feet. Okay. So what we're really after, though, is what is the rate of change of the area with respect to time? And so what we can notice here is that, again, this is for every 1 foot change in the radius, the area will increase by that much. But how much is the radius actually increasing every second? It's increasing by 3 feet per second. So really what I want to do is multiply this thing by 3 to figure out how much the area is going to change for every second. Okay? And again, if you look at the units on this thing, the units of this we said were feet squared per foot. And then if I multiply this by this, this was 3 feet per second. So look what happens. The feet cancel, and what am I left with for my final units here? Feet squared per second, and that's exactly what I want. The question is, how much is the area changing for every second that goes by? And so feet squared per second matches the units that I have here. Okay, so what we get then, this is really the foundation of the chain rule here. The rate of change of the area with respect to time is the rate of change of the area with respect to the radius first, and then we multiply that by the rate of change of the radius with respect to time. Okay, so again, the rate of change of the area with respect to the radius, that was 2 pi r. So that's this, 2 pi r. And then dr dt was 3. So this becomes 6 pi r. But really, we would like this to be in terms of time. So if you notice here, the r that I have was actually a function of time. That's 3t. So I'm going to get this is equal to 6 pi times 3t, which is 18 pi t. So again, I had two functions here. I had an area function I guess you can say, remember the area was pi r squared. And really what I did was I took the derivative of that, a equals pi r squared. That was where the 2 pi r came from. So that's this dA dr. That's the 2 pi r. And then the r was itself a function of time. So that's 3t. So then I multiplied by its derivative here. That's the dr dt. Put those together and I got this. But then I have to also remember that r was a function of time. So I changed it. And then I just multiplied here. So I know this is probably a little bit confusing when you first see it, but hopefully with a little bit of practice we'll see sort of how this works more in the context of word problems.